Hello viewers, welcome to my channel KK Concepts of Electrical Engineering.
Now, application of Maxwell's equation to determine the boundary conditions. So we have already found out the boundary conditions of electric and magnetic fields, but by using the Maxwell's equations, we will find the boundary conditions very easily. Now, let us find out the boundary conditions for electric field. Now, consider the boundary surface having the mediums, that is M1, and this is our M2 having epsilon R1, epsilon R2 are the permittivities of the mediums. Now, tangential component ET1 and this is our tangential component ET2. Now consider a rectangle closed path on the boundary whose height is, let this be delta y. Now applying Maxwell's equation derived from Faraday's law, that is closed surface E dot dl equals to minus closed surface dou b by dou t of ds. As delta y tends to 0, the area of the closed path also approaches 0, and hence right hand side becomes 0. This one becomes 0. Even the magnetic flux density B has finite value. Now, what happens to this? Then closed surface E dot dl equals to 0. Let this be delta x. Then we can write this as E t1 delta x minus E t2 delta x equals to 0, from which we can write E t1 equals to E t2. If one of the medium, let us say N2, is perfect conductor, then E tangential term 2 will become 0. Then this will become Et1 equals to E tangential 2 equals to 0 for the type of materials. Let this be our boundary surface. Now consider a small cylindrical Gaussian surface. This is dN2 and this is our dN1, so that this is delta S and this is also delta S, and the height of the cylinder is delta H. So this is medium 1 and this is medium 2. Maxwell equations derived from Gauss law, that is d dot ds equals to rho v of volume of dv. As delta H tends to 0, this cylinder will become a normal surface, which is nothing but volume becomes 0. Then this term will become 0, that d n1 delta s, the surface area of this, minus d n2 delta s equals to 0, from which we can write d n1 equals to d n2. In these two cases, tangentials of electric field intensity as well as normal components of flux density are continuous. Now consider this case, that if one of the two media, in our case that is M2, is a conductor, then dN2 is equals to 0, but rho s is not equals to 0. Then dN1 delta s minus dN2 will become 0 equals to rho s delta s. In this case we can write dN1 equals to rho s. For perfect conductor, finding boundary conditions for magnetic field, consider the boundary surface, and medium 1 is having mu R1 permeability. Here medium 2 is having mu R2 permeability. Tangential components now, magnetic field intensity HT2, HT1. From the Maxwell's equation derived from Ampere's circuital law, that is closed surface of H dot dl equals to closed surface J plus dou d divided by dou t of ds. Now, as the delta y tends to 0, then the displacement current dou d by dou t tends to 0 equals to 0. Similarly, conduction current J is also tends to 0, nearly 0. Then H T1 in this equation is L is delta x minus h T2 L is delta x equals to 0. Then from this 2 we can write h T1 equals to h T2. Consider one of the media, say N2 is perfect conductor, then what happens to h T2 will become 0. When this becomes to 0, J will be always there. Then we can write h T1 delta x minus h T2 became 0, so equals to J delta x. Now this is going to become h T1 equals to J for a conductor. But J's is surface charge density, so case A, case B. Now if this surface is a current sheet of current density Js, then this equation now h T1 delta x minus h T2 delta x equals to Js. Now from this we can write delta x h T1 minus h T2 equals to Js. Consider a cylinder on boundary surface having height of delta h, and medium 1 is having mu r1, medium 2 is having mu r2. Then from the Maxwell's equation derived from Gauss law, that is b closed integral of beta ds equals to 0. When delta h tends to 0, now we can write b n1 delta s minus b n2 delta s equals to 0. From this, b n1 equals to b n2. So normal component here, it is continuous. In this case, tangential component is also continuous. Then this is perfect conductor in medium 2. Then ht1 equals to js. When there is a sheet on the boundary surface, then you are going to get ht1 minus ht2 equals to js.
If you have any suggestions and queries, please mention in the comments. If you like this video, please like, share and subscribe. Thank you for watching the video. Please stay tuned for more videos.